Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Evgeny Korneev. Evgeny Korneev received his bachelor degree in applied mathematics and physics at MIPT this year. His thesis developed in IITP was devoted to the development of video quality adaptation algorithm for cloud VR. Now he continues his work at Wireless Networks Lab at IITP, focusing his research on improving the quality of cloud VR applications. Evgeny, the floor is yours.
Thank you. Good evening, ladies and gentlemen. Before I begin, I would like to thank you for coming and ask to hold the questions until the end of the presentation or some logical part of the presentation, since I deal hardly with interruptions. Thank you for understanding. Okay, so now we are ready to begin. As it has already been mentioned in the agenda, today's seminar will cover the traffic of cloud VR applications and related topics. First, I will touch upon some general VR topics, such as the history of VR and the state of the art. Then I will introduce the testbed used to gather traffic samples. Third, I will talk about modern video codecs and the structure of the video bit stream. Next, the obtained results will be presented and thoroughly explained. Finally, I will introduce the developed model of the VR application that carefully employs the results of our research. Before we dive into technical details, let us briefly discuss the history of virtual reality. It is considered that the first prototype of a VR system was developed by science fiction writer Stanley Weinbaum in 1935. In his story, a professor comes up with a new invention. The participant wears goggles that display an immersive reality, where a story happens around the spectator and not just on the screen. The participant can see, hear, and taste the world he dives into. This story described the VR system that engineers are still trying to create, the ultimate goal. Since the time of publication, people have invented different devices trying to place a spectator into such a real world. Nowadays, computers are playing an important role in delivering the VR experience to the users, who can already participate in the story around them. Until recently, there was an issue. The picture was delivered to users via cables connected to their head-mounted displays, thus making careless gamers look like this. Unfortunately, the problem is a bit deeper than it looks like. Dangling wires not only break the illusion, but also can lead to serious injuries. However, immersive VR requires intensive computers, so for now it cannot be simulated directly at the headset. Cloud technologies are employed. A remote server renders the video stream and sends it to the headset, which merely displays the picture to the user and sends its actions back to the server. To improve the user's experience, wireless technologies should be used to deliver data to the users. As it will be shown later, several gigabytes of video data per minute should be delivered to the user with a low delay, setting new challenges. To enable more efficient VR services, an elaborate and extensive model of a VR application is required to be developed. This model can be used to estimate the impact of quality of service parameters, such as throughput, jitter, or packet delivery reliability, on the quality of experience of the end users. A few existing models of VR applications lack accuracy and extensibility. The ones that we found didn't model many issues that we found during the research. For example, first work in the list uses an application for a mobile phone as a reference VR system implementation, something like Google Cardboard. Such applications use a mobile phone to display the video to the users, and the phones are usually less powerful than specialized VR devices. The authors of the paper captured the real traffic, but they didn't analyze it and modeled the traffic as is, just as a sequence of packets captured during the experiment. They also suggested a distribution of inter-packet intervals, but the real VR systems mostly consists of streams that have a well-defined structure. The second work mentioned on the slide didn't pay significant attention to the traffic structure either, and just models it as a sequence of random requests that must be satisfied before a certain deadline, thus ignoring the inter-packet correlation too. As I have already mentioned, we studied a real enterprise-scale application. To be precise, we used a Pico Neo 2 headset and StreamVR gaming platform to play the game named The Lab. It is a cartoon game with a rather dynamic gameplay. The headset of the choice supports 6 degrees of freedom. It tracks both the location of the user's head and its direction of view. As a result of our research, we analyzed the structure of the traffic generated by the VR application, modeled it, and developed a simulation model of a VR application. We applied this model to estimate the quality of experience for the considered application and for the one generating the bitstream according to the state-of-the-art recommendations. Okay, now we can move on and talk more about technical details of the research. And the first topic to be covered is the setup used to gather the traffic. We used a powerful desktop to stream the VR game. The researcher wore a head-mounted display, or HMD for short, that was connected to the PC via a Wi-Fi access point with 802.11 AC standard running on it. The access point was connected to the PC with a wired link. We used the Wireshark sniffering tool on the PC to peek into the transmitted and received data. The Pico headset ships with its own streaming application responsible for pairing the HMD with the computer, sending the video stream to the headset and receiving the feedback. It is called Pico Streaming Assistant and acts as a middleman between the HMD and the SteamVR platform. So with this clarification, I can add that the transmitted bitstream was captured between the access point and the streaming assistant. Here, to give you the sense of the traffic load, I would like to mention that 1 minute of the gameplay generated from 1 to 2 gigabytes of data. Good. Now we can discuss the captured data. Please note that Pico Streaming Assistant is not a software designed for the large-scale deployment in the cloud. Instead, the developers expect that all the interactions are happening inside local area networks. Therefore, the used network protocols are very simple. The headset uses UDP protocol to communicate with the PC. Several UDP streams were found. 3 of them carry RTP frames, and the other streams data was not well recognized. First, I will briefly describe the unknown streams and in the end turn to the video streams. I will refer to the streams directed to the HMD as the downlink and the opposite as uplink. Okay, the first one is an audio stream. It is a relatively lightweight downlink RTP stream of data consisting of pairs of packets of the same size sent every 10 milliseconds. The average bitrate is around 1.5 megabit per second. Another downlink stream of UDP packets with the following CDF of inter-packet times. The bitrate equals 15 kilobit per second. Probably these are vibration comments sent to the handheld joysticks. 2 uplink UDP streams of packets of constant size. The dispersion in inter-packet times is caused by the channel access delay. And here is probably the most interesting stream among the undecoded ones. It is an uplink stream of data having bitrate around 20 kilobits per second. We assume that it describes the head's position. And On this slide, you can see CDFs for the packet sizes and inter-packet times for this stream. And finally, the last UDP stream of currently unknown nature. It consists of strictly periodic packets of the same size sent from the headset to the PC each second. We still cannot determine its purpose, but it is very light, so it has almost no contribution to the aggregated flow. Now, before we move on to the discussion of the captured video data, I will digress a bit and tell you about the video codecs, because later I will refer to the terms and entities involved in the video coding process. I will cover the most recent and popular video coding standard called H265, or High Efficiency Video Coding, HEVC for short. Let us begin with the general terms used by the standards. First of all, there is a picture, or a frame, that is to be coded. When the picture is being coded, it is divided into chunks of data that are packed in a bit stream with supplementary information that helps to decode the compressed video data. Each chunk is packed into its own network abstraction layer, or NEL, unit that carries some high-level information about this chunk, such as its type. The video is not just a single picture. It is a sequence of closely related pictures. Thus, a new frame can be described not only on its own, but also has as a difference relative to the other frame. Thus, there are 3 types of such pictures: intra-coded frames, or I-frames, predicted frames, or P-frames, and B-predicted frames, or B-frames. The relationships between the pictures are shown on a slide. I-frames can be decoded independently from any other frames, and thus are relatively big. P-frames are decoded based on the previously decoded picture, and are generally smaller than I-frames. Finally, B-frames are coded in a different order and require the latter frames to be decoded, and thus are only used with buffered video. VR applications cannot use them because of the latency constraints, so I will not talk about them anymore. The downside of such a scheme is that P-frames will propagate artifacts once a decoding error is encountered. To alleviate this problem, the video is divided into so-called groups of pictures, or GOPs, repeated sequences, of an intra-frame with several predicted frames following. Often, intra-frame insertions refresh the decoder frequently, but make the bit stream heavier. To encode the changes in the picture, the video encoder splits it into small square regions called coding tree units, or CTUs, and encodes the changes inside them. Then these regions are grouped into slices, containing an integer number of those regions in scan order, as pictured on the slide. For example, you can see here a picture divided into 2 slices. It is also worth mentioning that each slice is independent from the other. On this slide, an example of partitioning the picture into CTUs presented. The size of a CTU can be up to 64 pixels wide. Okay, on this slide, you can see a familiar picture, but with several additions. The basic squares are, again, CTUs, and the line in bold divides the 2 slices. However, HEVC allows slices to be divided further into slice segments whose boundaries are denoted with dotted lines. Look at the top slice. It is divided into 3 slice segments. The first one, filled with blue, is so-called independent segment that can be decoded, as you can guess, independently. The 2 subsequent segments are dependent segments and can only be decoded after the previous one. The bottom slice consists of only one independent slice segment. Each slice segment can be packed into its own NEL unit and transmitted independently. Such a partition of slices into segments allows to decode a part of a slice, even if a segment was lost. If a slice was transmitted as a whole, one lost fragment would cause the whole slice to be discarded. HEVC was developed with efficiency in mind, and it naturally supports parallel encoding and decoding. The HEVC's predecessor, advanced video coding, indeed divides a picture into roughly horizontal slices only in scan order. HEVC introduces tiles, rectangular areas of a picture, each having its own scan line. Each tile carries little overhead compared to a slice and can too be decoded independently from other tiles. The introduction of tiles primarily enables dividing a picture into almost arbitrary parts to better balance the load between encoding cores and utilize spatial information more efficiently. There are two constraints, though. Each tile should only contain complete slices, or a slice should only contain complete tiles. For example, on the left picture, you can see one slice divided into two tiles vertically. On the right, the same two tiles, but this time each divided into slices. The left tile consists of two slices, and the right one consists of one slice. It is known that rare birds negatively impact the network performance, and the structure of the video stream is inherently bursty. One of the technologies that mitigate this problem is so-called inter-refresh. It is not an HEVC-only feature and was even developed for earlier codecs. Imagine a picture split into 4 horizontal slices with intra-coded blocks colored in yellow and predicted blocks in white. You can see the traditional GOP structure on the left and the video stream structure with inter-refresh enabled on the right. Inter-refresh introduces infinite length GOP. It just means that all the frames in the stream are predicted, but a part of each slice is intra-coded. Inter-refreshed stream successfully refreshes the columns of the picture, and thus still any error will be cleared within 4 frames, just like in case with a traditional GOP structure. The benefit of inter-refresh is described on this slide. Since the size of an iframe is usually significantly bigger than the ones of p-frames, the bitstream's intensity varies in time as demonstrated on the plot below. Once in a GOP, there is a burst of intensity. The inter-refreshed video, on the contrary, makes all the pictures have approximately the same size, thus smoothing the bit stream. Now we can return to the most interesting part, the video streams. First of all, we found dependent video streams. We assume that each one corresponds to each eye of the viewer. The GOP structure can also easily be guessed by just looking at the CDF of frame sizes, but more on this later. The Pika Streaming Assistant supports several video quality settings and screen refresh rates. The following example corresponds to the standard settings and 72 Hz refresh rate. Other streams are similar, and the main differences will be presented separately. Okay, let us focus on one stream's structure. On the slide, you can see the sizes of the packets sent. Let us assemble those packets back into frames. The frames are much bigger than the MTU, so they are fragmented. The packets belonging to the same frame are sent almost simultaneously. You can see in the upper part of the plot that several packets of the same size are sent together, and there is one last packet of less size that carries the remainder of the frame. The time spacing between the vertical lines also suggests that we are dealing with frames. The packet groups are sent each 14 milliseconds, which corresponds to the FPS of the pick streaming assistant. The repeated group of packets in the bottom part of the plot will be described on the next slide. In the video stream, there are rather big pictures sent repeatedly. You can see them in red circles. As you may remember, the bigger frames usually correspond to the iframes. Each iframe is followed by 4 smaller frames, p-frames. So we now understand that the length of the GOP structure equals 5. The video bitstream consists not only of the coded video data, but of some supplementary data too. Those 3 packets sent in the beginning of every GOP correspond to the NEL units that describe how to decode the pictures. The information in those packets has hierarchical structure. The first packet is called picture parameter set and describes how to decode a single frame. It refers to the sequence parameter set, or SPS, that is applied to the whole GOP. And finally, the SPS refers to the video parameter set, that in turn applies to the whole video stream. Note that this information is sent repeatedly, so even if a packet is lost, within a GOP, a new copy will arrive. Here you can see the CDF of the sizes of frames. The 2 modes are clearly seen. The first one is precisely 4 times of the second, indicating the GOP structure again. Each big iframe is followed by 4 small p-frames. This slide demonstrates the bitstream, the bitrate of the bitstream. It is relatively constant and is around 40 megabits per second. Now, when we reassembled each video stream, let us see how the 2 streams interact with each other. The frames belonging to different streams are not sent simultaneously. At this figure, you can see the time intervals between successive frames. Let us arbitrarily assign numbers and colors to the streams so that I can refer to the streams faster. The first stream will be blue and the second one red. Look at the rightmost 2 lines, the red one and the blue one, that have almost merged. The blue line describes the time intervals between successive frames belonging to the first stream. The red one to the second stream. As we could have expected, the average time interval is around 14 milliseconds, which is an inverse of 72 fps. The purple line, the leftmost, demonstrates that a frame of the second red stream follows a frame of the first stream within 3 seconds. Similarly, the yellow line tells that the blue frame goes 11 milliseconds after the red one. Again, as it could be expected, the sum of these times equals 14 milliseconds. Finally, we can merge those streams and imagine one big bit stream which is twice as large. We can then plot the CDF of time intervals between successive frames and find the green line in the middle of this picture. Actually, it is just the sum of the purple and yellow CDFs. Recall that I have mentioned that streams are independent from each other. Our experiments show once the game begins, the structure of the two streams remains fixed, so that the blue and the red lines remain the same. But during different games, the streams randomly shift relatively to each other, and thus the yellow and the purple lines, and therefore the green one, will move. Well, now we have discussed everything related to the 72 Hertz standard video stream. And on this slide, you can see the other stream's characteristics. I can note that the fast quality settings reduce the amount of transmitted data significantly, but the visual quality suffers as well. It is also interesting that the HD settings use GOP length that equals 37. Now, the parameters of the Pico video stream can now be summarized as follows. First, every picture is coded as a single slice. Second, Pico uses the GOP structure of a fixed length. That depends on the streaming assistance settings. Third, Pico doesn't use inter-refresh. NVIDIA provides with the following recommendations to code in video streams. First, it suggests using several slices, of course. Second, it insists on enabling inter-refresh and thus using an infinite GOP length. To compare the impact of the coding technique on the user experience, we prepared two types of video streams. First, we encoded the video as Pico does, using the parameters obtained from the experiments. And second, we encoded the video as suggested by NVIDIA. And then we simulated the video transmission using our model with a P2P reliable link, so that the frame losses are only caused by frames coming too late. And here are the results. In the experiment, we varied the throughput of the P2P link between the server and the headset. The left figure demonstrates that to transmit the Pico-coded video without losses, one must use the link with bandwidth exceeding the bitrate of the video stream. On the contrary, it is enough to have the same bandwidth as the bitrate of the NVIDIA-coded stream to satisfy the delay constraints and deliver all the frames in time. Now I can sum everything up. First, we discussed the latest video coding techniques. Second, we disassembled the video stream generated by the modern VR application. Then we developed a simulation model of VR application. And finally, we applied our model to two different video streams to see whether some advances in video coding can improve the quality of experience of the end users. Thank you for your attention. I will be glad to answer your questions now.
Thank you, Evgeny, for your presentation. Could you explain whether you only guess at the structure of the video streams in your testbed by taking into account sizes and interframe spaces or interframe times of the packets, or you do some deep packet inspection or decoding some null units or something like that.
I see. Thank you for your question. Probably I can go back here. I have mentioned in the beginning that there are actually two types of streams, undecoded ones and, well, let's say decoded ones or video streams. Undecoded ones are so called because we have actually no idea what is transmitted inside those packets. So we can see the UDP headers and we cannot guess the payload of these UDP streams. And here is the completely different story with the video streams. We already knew that the UDPs contain RTP packets. So we had then a task. We had to determine which coding standard was used so that we could decode it later. Actually, I can see whether I have a picture. Yep, I have this one. So this is what we had to do. We could see the RTP protocol, and we had to, well, at first we had to guess what is transmitted inside them. Actually, we, let's say, succeeded in guessing and found out that this one, well, the codec was used is HEVC. So that after that, we could decode the headers of those null units, since we know that here is the null unit header. And then we could get the clear picture which frames are sent at which moments of time, so that we can now be sure that those packets are indeed iframes and these are indeed p-frames. Did I answer your question?
Yes, thank you.
Thank you for the question.
We have questions in the chat.
Of course. Let me check it. Ilya Levitsky asks, the first question is on slide 14. Does the pattern of the traffic indeed depend on head movement? Slide 14. Let me move here. Well, actually, it is rather hard to determine because the head of the user moves constantly, and even subtle movements can cause the picture to change dramatically. So we cannot really tell whether the traffic really depends on the head movements. But still, I think we can try to think over some, or how to set up an experiment to check it. Thank you for your good idea. And the second question is on slide 16. Can those be hello signals? Well, probably they can be, but still there is, I cannot see why they should be sent, because the streaming assistant has already paired the headset and the computer, so they already know who they are, and they don't actually need to maintain a connection, since already a lot of data is transmitted in uplink and downlink. Have I answered your questions?
Yes, thank you.
Thank you for questions. And Dmitry Bankov asks, does the encoder produce all the packets for a video game for one eye at once, or is it a continuous process? If I understand you correctly, the decoder, or the encoder produces frames constantly, because this is, well, this is an interactive game primarily, so that the game and the actions and everything the user sees, it depends on the user's actions. Thus, the server cannot encode all the video in advance, and it has to wait to the user's actions, user's movements, and then encode the video accordingly.
I also have one more question. You mentioned that when we change game session, that video streams for HI may shift somehow, or and this is the only difference between game sessions which may happen. Could you comment, maybe if we play another game, not that you mentioned, maybe we have some different results, or?
Okay, probably I'll try to rephrase the question. You're asking whether this picture will be relevant to a different game, correct?
Exactly, yes.
Okay. This is actually a rather good question. And I think that the answer is yes, because as you can remember, the streaming assistant is the software that controls the frame rate and the video quality settings. Thus, independently from the game that is transmitted to the user, there will be relatively similar streams of packets. So they will be sent with the same interframe interval, and they will form those structures. Probably the other difference that can be encountered is related primarily to the sizes of those frames, because different games require a different amount of information to transmit. For example, I can demonstrate this picture. You can see that it is rather detailed one. On the contrast, for example, some other games like Minecraft might need much less data to transmit, so that the frames will take less space, and it will be easier to transmit them. So they obtained results for the different games would be different in this plot primarily. Those slopes will move right to left depending on the detalization of the game. And the overall structure that we can see here will remain the same.
I guess it may depend not only on the picture of which game of the game, but also on the settings of the used encoder. And do you test some other games using your testbed?
Well, we did play different games, but again, the streaming assistant only support these settings. So we can choose between fast, standard, and HD video quality, and two screen refresh rates. Actually, a different game will produce different frames, probably, but still the generated traffic will be the same, since it is streaming assistant who cares about the encoder settings.
Okay, thank you.
Thank you.
Evgeny, can I have one more question?
Of course.
So, as I understand, to transmit two video streams that are almost identical, we could use some type of encoding that would transmit some data which is common for both frames and which also carries the difference between the two frames, so that we did not need to send pretty much the same data twice. Do you know if such encoders exist, and if so, have you witnessed them in your headset?
It is actually a really good note. Well, we didn't see these encodings in our experience, but well, yes, now such encodings are under active development. So one of them is the successor of HEVC decoder, well, coding standard. And well, these codecs not only reference this particular problem that we have to transmit to almost identical streams, to almost identical pictures. They also reference the problem related to the fact that the user, well, it can see the picture that is located around him, so he can move his head, and he needs some sort of 3D encoding. And currently, the HEVC encoder only supports 2D encoding. So yes, there are codecs that are working on the problem you have mentioned. And if I'm right, the correct name of this standard would be H266. But it still remains under active development, and we haven't seen the draft of the standard yet.
Dear colleagues, maybe I would like to first I would like to thanks for the very informative presentation. But about this last question about actually this technology is known. It's 3D encoding, and it is known in disks maybe for 8 years from now. It's if I remember correctly, the correct abbreviation is MEVC. But it is using AVC as a baseline.
Oh.
Yes, but such codecs exist. Maybe my example is not real-time encoding, but certainly such codecs certainly exist.
Well, then
already.
We will check it out. Thank you very much for the note.
It's just 3Ds, for 3D videos.
Okay, thank you very much.
So to continue my question, if for now we do not see some mutual, common or difference information between the two frames, so as far as I can tell, you see that the VR traffic is mostly described by two identical video streams, and everything else does not contribute too much to the traffic load. So is there anything fundamentally different about VR traffic compared to simply assuming that it is just two identical video streams?
Thank you. It is also a good note. Actually, the VR streaming is a really, well, it is really sensitive type of streaming in terms of the delays and the playback times. Well, when people are usually talking about the streaming applications, they often refer to such things as YouTube streams or something like this. And in such cases, a delay of, well, 2 seconds or 5 seconds will not be really noticed. And in case of, well, the VR videos, the feedback from the headset to the server must be delivered really fast, and the server must react quickly, generate the new corresponding picture, and send it to the user within, well, within 50 milliseconds, definitely. So time constraints are a big issue when we're talking about the video streams related to VR games. And well, yep, as I have mentioned now, the feedback should be delivered quite reliably and well, with low delay. This is actually one of the reasons why the cloud technologies are employed, since a lot of computations must be done in very short time periods. And well, handheld devices or even the HMDs, they still cannot process these amounts of data.
Okay, I see. Thank you very much.
Thank you. Here's a question from Ruslan Yusupov in the chat. Could you please comment once again why NVIDIA settings were better in the numerical results? Well, actually, we can see here that NVIDIA settings require the throughput of the link between the server and the application that almost equals to the bit rate of the stream. Actually, this happens primarily to the effect that I have mentioned earlier. This happens thanks to the inter-refresh. So the Pico codes videos like this. It is a standard approach. And the NVIDIA offers well, a new approach and suggests coding videos using inter-refresh. And here you can see that here are some, well, moments when the load is high, and then we can see that almost no information is sent over the channel. So that to deliver all the frames reliably and in time that belong to the Pico stream, we should deliver these frames in time primarily, since all those little frames will be are much easier to deal with. And when we are taking the bit stream generated by the codec with NVIDIA settings, we can see that every picture is almost identical. So in general, we need much less throughput to deliver every picture in time. So primarily the problem, let's say, with the Pico stream is in these peaks. So, well, the most important intra-coded frames are sometimes delivered out of time and must be discarded. Hope I answered the question.
I have one more question. As I understand, you conduct all the experiments with your testbed in somehow ideal conditions when you have zero loss ratio and the channel bandwidth used for transmission is much higher than the bitrate of the video streams. Have you conducted some experiments with non-ideal channel conditions. For example, when you have some losses on some links between the headset and your PC, and or maybe some limitations of the channel bandwidth.
Thank you. I would like to clarify whether you are talking about the simulations or the real experiments conducted with the real testbed.
I'm talking about testbed.
Okay. And then, yep, somewhere here. Yep, we used, well, we conducted an experiment in rather ideal situation when our access point was capable of delivering all the traffic in time. And yes, we have tried to manually increase the delays, increase the packet losses, and some other things. And well, generally those results are not formalized enough to be, well, discussed here, since we cannot tell about the real causes of the problems. So, well, let me paraphrase it.
So I guess it's just ongoing and not finished research yet.
Well, yes, correctly.
Yeah, I understand. Thank you.
Thank you.
Okay, I guess that's all questions for today. Thank you, Evgeny, for your talk. Also, I want to thank all participants of the seminar for attending. The next seminar will be held next week at the same time. At this seminar, Professor Jérôme Femei will present us a talk about wireless interactive VR using millimeter wave communications. Thank you. See you next week.
Thank you for your attention.